Okay, hello everybody. So now I'm gonna start today's recording, and today is August 6th, and today's what I'm gonna do today is a little bit different from previous days. I'm gonna watch this CXL. So CXL stands for Computer Express Link. This is some technique that is promoted by Intel's, and they just abandoned this optimum persistent memory technique because they can't get a profit out of it. So this is a technique that maybe there's some potential here, and the reason why I watched this video is because there is a proposal that is written by Zhichao that wants to submit this proposal to the Intel to get the CXL machine back so that we can do some experiments. Okay, so I want to watch this video to get something background knowledge from here. Okay, so let's begin. Okay.
A bunch of these questions here that were just asked are right in line with what I was going to talk about. And actually, I'm not talking a bunch about our CPUs. Everybody knows that Intel has our CPUs, and we've got CXL support, and we're active members of the consortium, and definitely trying to make this a successful transition. But my emphasis is really more about CXL as being a revolutionary new technology as opposed to evolutionary. And the enabling efforts that go into that are significant. And I like to say it takes a village, and we are that village. The people who are at this conference are the village that needs to make CXL happen. So we have a strong upswell. A lot of what was just spoken about it has to do with the industry support and the activities behind it. But a lot of the things that have to happen, such as the software to support all these new use models and the memory tiering that has largely been done, at proprietary accounts to this point, is now public. It's now, a standard, and the effort needed to do that continues.
Okay, so stop here. This guy mentions that there is software opportunities, and when we utilize the CXL techniques, so this is a good point. Let's see how he elaborates this.
So really my emphasis is on industry enablement and what it takes to make CXL successful. So in the interest of a little time and hopefully to get you all to eat today, I'm going to be pretty quick with these. A few of these slides are exactly what CMAC just showed. So I just wanted to show not just whose the companies are, but the diversity of these companies. It's not just CPU vendors or memory vendors or hardware vendors that are doing all this. It's a wide variety, and it spans the industry, and it's actually very impressive. If you've been involved with any standards organizations over the years, this list of companies is about as comprehensive as it can get. And that's going to continue and is necessary to make CXL happen. Similarly, this is also another slide that Simak just showed, and I wanted to show that not only is it those core companies that are members of the board, but all these other companies are coming up with hardware solutions, filling in the gaps and finding the use cases that need to be fulfilled. Many of these hardware companies at the bottom are developing products that previously didn't exist. There's adding functionality into those switches that may not be there. Key issues with industry enablement. And by the way, I didn't say it at the beginning, but for those that don't know, I work for Jim Pappas, and many of you know Jim Pappas. He couldn't be here. He asked me to say hi, by the way. So Jim expresses that he had a saw that when CXL came out, I was able to solve it a little quicker than we might have otherwise done it. The headwinds are less. And then this is also the last slide of CMAX that I'm going to show, and I just added at the bottom the crawl, walk, run. So there were some questions about when it was going to happen, and I think from our experience with all technologies, for example, I'll give you an example, is PCIe 5. So PCIe is what we'd consider not a revolutionary technology, but evolutionary, right? We already talked about we have PCIe 1, 2, 3, 4. We get to 5. It's a speed bump. Sometimes, like PCIe 6, for example, is adding some complexity there, some new things, some new changes in the software side. But really, PCIe 5 is largely a speed bump. So the validation.
And I'll just repeat his words. He's saying that PCIe is a evolutionary techniques because of the speed, but not a revolutionary because this just speed bump, nothing else fancy. I think this is what he means.
And the productability of that, I don't know if that's the right word, but is pretty predictable. We go through, we test the new speeds. There's a lot of hardware, the SI side of it. We make sure that there's nothing breaks as far as timing goes and things like that. But it's pretty straightforward, right? CXL is very different, and in this case, we really do need a crawl, walk, run. So CXL 1.1 has come out, a lot of POCs, a lot of demos, a lot of testing to see what's necessary, a lot of identifying the gaps that we have to close, significantly in software in particular. Because all those proprietary solutions now have to go to the masses, and they have to go to the standard distribution operating systems and standard tools, right? So as we go through 2.0 and 3.0, I think that's what we're going to see is Walk's going to get many more deployments. When we get with CXL 2.0, there will be definitely end users and customers that will be deploying CXL 2.0 in the wild, so to speak. And then with CXL 3.0, we really see it broadening out. And this goes from both the number of hardware devices that are available, the number of CPUs that are available that support 2.0 and then 3.0 will expand significantly across that time frame. And clearly, the software and the support tools to get there, the market will be there as well. So this is just a kind of a catch-all slide showing all these complexities I'm talking about. So, getting the new revolutionary technology, it requires obviously the hardware developers, and we have to get their silicon in hand. And by the way, that is in hand. And if you haven't seen it, there's a number of demos over in the booth showing some native CXL silicon now, as opposed to FPGA implementations. Please go look those up and talk to those vendors. They're doing great work, and they're leading the charge here. The IP providers, of course, have been working for a long time. They go into all those hardware silicons. The controller vendors oftentimes are not productizing their product directly. They're doing similar to a drive controller and an SSD. They're doing that front end controller, but then somebody else is going to take their product and validate it and sell it. And that adds complexity to the level of validation we have to do here, right? And then obviously the product vendors. And then on the other side is the stuff that's really new for a revolutionary product. The software tools, Memberge, what they're doing, all the efforts that they're putting into testing and developing use cases that are viable in the market. If it wasn't for that, this would largely remain a niche, or more precisely, companies that own their whole stack that can write and develop and do their own tiering and do all that, the memory manipulation that's necessary to really benefit from this as much as possible. But now these other solutions are coming out, it becomes a standard. Everybody gets tools, we test it at different levels, and we can tier up the memory. And obviously the peer-to-peer solutions add to that as well. And those are coming in parallel. And operating system support and the drivers for the devices, that goes kind of without saying, right? That those are necessary to make it work. And then the applications, as mentioned, the Memberge, how are we going to use this? What level of tiering are we going to do? When sharing is happening, how is that being managed? At what level? All those come into play here, and that's another level of validation and enabling that has.
So I also want to do a quick summary, and what he says is that the problem here is how to maintain the coherence of different memories from different nodes, right? And this slide, he wants to tell us that how this CXL technology just came from some standards and consortium and to the industry adoption, right? We have a lot of steps to go through, like we need to get operating system support, we need to how to write drivers, right?
Has to be done. Another comment I guess I'll make here is the validation of CXL, because it's different. This is memory specific. It's not the same comparison when we're talking about accelerators and peer-to-peer devices. But DDR is basically done with large configurations, and historically the DDR controllers have been in the CPUs or controlled by the CPU vendors, one of the two. And so that validation largely gets done by the CPU vendors in partnership with the DDR vendors directly. It's a one-to-one partnership. Full validation, everything possible gets validated, and if it's not validated, it's not supported. PCIe, on the other hand, is opposite of that. It's done through the SIG. Largely, the compliance is done through the PCI SIG, and all CPUs have to test and validate pretty much everything. And so what happens is you get a broad brush of what's validated. Occasionally, there's a product that comes along that wasn't validated, that doesn't work. That gets debugged and solved iteratively, but it gets done because it's a large open socket situation. CXL is kind of a combination of the two, right? There's DDR behind a controller, but it's external to the CPU. So now the CPU, the various CPUs are focused on testing, that interaction with that controller. But what goes on behind it is largely outside of it. And yet those companies in the past, controller vendors for DDR memory have been CPU vendors for years, right? So these new vendors that are doing these controllers need a lot of help, and gladly and luckily, or not luckily, intentionally, the CPU vendors are heavily engaged with those companies doing these controllers. Both Intel and the other CPU vendors are engaged, trying to make sure that validation gets done well, so that it's reliable and the solution in the end is as robust as it is coming out of the CPU. The end result, I think, after a qual rock run, after we get to that, PCIe or CXL 3.0 time lane, we're going to see CXL modules and CXL devices being largely like PCIe devices, where they're tested, it's an open socket, if there's an issue it gets solved, and the industry becomes robust in that manner, right, where it can handle everything. Initially, I think it's going to be a little less than that. I think there's going to be some limits on what's validated and tested, a little bit more on the DDR side, where initially we're going to have to say these CXL devices work and have been validated, and deploy them at your will and however you like, and then I think as we get farther down the road into the run stage, it'll become largely PCIe-like. So it is a different paradigm, right? We've never had this before. We've never had a disaggregation of memory controllers like we're going through right now, and it's.
And he talks about a desegregation of memory controller. I really doubt about that. How is the speed, right? How can this CXL technology maintain the speed like DDR, right? 64 gigabytes bandwidth? I'm really curious about it.
It's non-trivial, but luckily, really the industry is coalescing behind this. And then one other comment here, this is kind of some details of what I just talked about, the different validation going on at the different levels. The one on the left is what the CPU and host do. The one in the middle is what the CXL module vendors, the memory module vendors are going to do, what they're going to focus on, the level of validation and functionality that they're going to try and ensure is robust. And then on the right is what the end users and the OEMs are going to do. They're going to take these systems, they're going to integrate them into their CPU host and switches and all the memory modules they want, and then they're going to use their software on it, make sure that it works in their use case. So it's a three-tiered approach, to be certain, and again, I think we've got great momentum behind this, but we're not done, so we need to keep doing it. A little comment in the middle there, if you're seeing what the green box is that we are trying to also
I gotta tell that this slide looks ugly, and the fonts and the words is too small for me to see clearly, and I just see the three pictures. My main focus, is just on the three pictures and what's the relation between them. I guess this is because we have a CPU and host, and then we have a CXL memory module that will connect it to the DRAM, maybe, right? And finally, we have what is this? OEM. I don't know what is this.
Because this is happening and it's going to get bigger and bigger and bigger, and we're all going to benefit. So hopefully that was helpful. Any question? It's actually, CMEC can maybe, I'll answer for him, but the consortium is there's already a working group, a compliance working group in the consortium, and the testing has already started, actually. The developing test suite is there already. I don't believe there's going to be a tested compliance list until 2.0 deployment. Is that right, CMEC? Or
no, I didn't learn much from it. What I did learn is that CXL is a technology that will combine the disaggregated memory into a whole unified memory that just looks like unified to the outside world, right? And the problem here, I think, is how to maintain the coherence, right? Because the memory in one node may be modified by another CPU in another node. So, and because of this sharing memory pool, we have some conflict resolvement need to be done. So I think I will adapting keep the store to desegregated. Essential steps to employ the red read and write from. And secondary store remain tally couple. Adapting key value stores. They typically refers to the. So what I want to do right now is to add WAL right hand log related adaptation to this paragraph so that this guy can get what he wants. He wants WAL to be added into this proposal, right? And I'm gonna add it. Adapting key value stores like to the desegregated infrastructure with high performance, high efficiency, good words, and high service quality, like separating WAL and secondary storage. Is a essential step to deploy and optimize applications and services. Backed by key value stores, secondary storage, I think I will add this to here for example. It's only temporary passed without formatting. Define clear formatting. Clear formatting. Now typically the legacy deployment is much stabler. Stores are reads and write files from local SD base. It's much stabler. CXL switching more like a generation, especially addressing the read performance penalty. You start to disagree with the secondary cache become orders of compute. Able to share the high memory secondary. Can we format this? Suggest edits. Format options. Select all. Hundreds. How can I add something here? I want to add a cross line that just might delete of the sentence. How can I do that? Clear formatting. High color. Insert format. I think I will just how about suggest edit? Suggest edit. You are suggest editing. You are suggesting? How can I do this? Hundreds to switch. At least we can tens of more hearts. Oh, I don't need to need. We can have as nodes that are connected to the same switch. With CXL devices. Is able to share. Second cache is the middle layer between storage. Display is a secondary read buffer to optimized as a secondary read buffer. This is interesting. Allows CPUs from different servers to share memory resources at previous impossible scales with cache. Okay. I think it's limited to a host being attached, unattached, and subsequently have a second host attached to the same device. The granularity might be smaller, say a Kubernetes pod, but the semantic is the same. From servers that is able to attach to a DAX device to share memory. like maybe we can elaborate this. Maybe can elaborate this by adding Kubernetes situations and specific CPUs brand that is capable of using attaching to X device like Intel Xeon.
Hey guys, Jamie.
Intel Xeon. So I'm also preparing for my TOEFL right now, right? So yeah, that's it. I'm also Intel. I'll Google it. What kind of a CPU brand that is able to attach to a DeX device? Intel CPU that is able to attach to a DeX device. CPU. Intel Optane CPU support. Let's see. Like secondary driver storage. Only reference it, not support. Series not supporting on 12th generation Intel processor. Make sure you have the proper driver version installed system for.
She wants the students to know. Now you might.
Acceleration from the table below. I see, so it is 11th generation. Could be use these PMAN devices, right? But it points out that Intel Optimum series not supported on 12th generation Intel. Why is that? Why is that? Removed from support by the Intel. Hardware products already reached end of life in production. The software will continue support. Will Intel continue to support these devices earlier? Oh, this is sad. So for now, all I can do is to support a chipset like this, right? I can add this. Okay, where is, oh, see. Intel generation processors and with chipset PCHLP. I need to pass this. I need to copy and paste this supported chipset. With chipsets. Elaborate this by CXL based. Share memory has slightly lower. '64. Oh, this is great. Hundreds of nodes. Switch to select device. Store some nodes. Simple to share. Nodes where hundreds of key value stored instances are deployed. That deployed. That are connected to the same switch as is able to share. Okay, great. So adapting desegregation. Like separating WL and secondary storage is separating and read sharing sharing memory pool.存算分离吗？是不是？ I think I should open this on another window to see if my editing anonymous crank. Yeah, I don't know about that. So one last time, I need to be the one who takes you home. One last time, I need to be the one who takes you home. Design and implement sophisticated shared memory. I need to do more research on this Express link, right? I want to know how it works. Computer Express Link is an open standard for high-speed central processing unit, 2-device and CPU to memory connection designed for high-performance data center computers. CXL is built on the PCIe physical and electrical interface and includes PCIe base block input-output protocol and new cache coherent protocols for accessing system memory and device memory. So what is the history? The specifications? Oh, we have a CXL 3.0. I need to do modification to CXL 2. Suggesting we have a 3.0, right? Because now we have this based on PCIe 6.0 physical interface and PAM4 coding with double the bandwidth. New features include Fabric's capabilities with multi-level switching and multiple device types per port and enhanced coherence with peer-to-peer DMA and memory sharing. Oh, so this is cool. But what about CXL 2.0? CXL specification 2.0 was released. The new version adds support to allow connecting multiple CXL 1.x and 2.0 devices to a CXL 2.0 host processor and or pulling each device to multiple host processors in distributed shared memory and desegregated storage. Contribution. It also implements device integrity and data encryption. There is no bandwidth increase from 1.x because CXL 2.0 still utilizes PCIe 5.0 physically. Release 3.0 was released based on PCIe 6.0 physical interface, multi-level switching and multiple devices per port. Okay, great. And enhanced coherence. Intel announced their family FPGA Support was announced for Intel's rapid processor AMD Zen 4 was shown. Standards, the main volatile memory, cache, and main protocol operate with a common link transition layer, which is separate from I/O protocol and transition layer. These protocols are multiplexed together by an arbitration and multiplexing block before being transported over standard. This is some words I don't understand for now. Device types. CXL is designed to support 3 primary device types: specialized accelerators, main general purpose accelerators, memory. Oh, I think this just this just mentions GPU, so we can actually access the GPU memory with CXL, right? This is cool. Memory expansion boards and storage class device. Memory expansion boards and storage class memory devices provide host CPU with low latency access to local DRAM and non-volatile. Type 2 implement 2 memory coherence modes managed by device driver. In device BIOS mode, device directly access local memory and no cache. Host the BIOS. The host CPU cache controller handles all access to device memory. Coherence mode can be set individually for 4 kilobytes page stored in a translation table in the local memory of type 2. Unlike CPU to CPU memory coherence protocols, the arrangement only requires that the host CPU memory controller to implement the cache agent. Such a symmetric approach reduces implementation complexity and reduces the latency. And CXL 3.0 replaces BIOS modes with enhanced coherence semantics, allowing Type 2 and Type 3 devices to back and validate the data in the host cache when the device has made a change to the local memory. Enhanced coherence also helps implement peer-to-peer transfers with a virtual hierarchy of devices in the same coherence domain. It also supports memory sharing of the same memory segments between multiple devices, as opposed to memory pooling where each device was assigned a separate segment. Okay, this is cool. So one segment could be accessed from multiple devices, right? CXL 3.0 allows multiple Type 1 and Type 2 devices. CXL 3.0 allows multiple Type 1 Type 2 devices per each CXL root port and adds multi-level switching, helping implement devices fabrics with no tree topologies like mesh, ring, spline, and leaf. Each node can be a host or device of any type. Type 3 devices can implement global fabric attached memory mode, which connects to a switch node without requiring direct host connection. Devices and hosts use port-based routing addressing mechanism that supports up to 4096. Okay, one thing I don't know about is that what is this fabric? What does this fabric mean? I want to Google it. Oh, this wiki is, this really update. They just update the time update the information in time. What is fabric? Clothes or other material produced by weaving or knitting fabrics. Global fabric. Computer. Fabric. Device fabrics. Computer science. Constructing a computing fabric consists of interconnecting nodes that looks like, I understand what is fabric computing now. It is a from my understanding, it is that fabric computing is just that a unified computing that consists of multiple nodes that do the same job at the same time, just like a supercomputer, right? These some are temporary. Global fabric attached mode. Okay, so now I have to change this. I have to change this nodes that up to previous sentences I wrote before reading CXL wiki. Up to hundreds of nodes for it is connected. Gen 0 6.0. So 6L up to 4096 computer server nodes, up to computer server nodes, servers that are connected with multi-level switches and deployed. Okay, I think this is good. because it mentions that here it adds multi-level support, right? Switching multi-device types per port and enhance the coherence peer-to-peer. Okay, connected with multi-level switches. With enhanced what is this? Enhanced coherence with peer-to-peer. Coherence with peer-to-peer. Peer-to-peer DMA memory. DMA and memory sharing. Okay, this looks good between storage and local. Data connected. Multi-level switches. So it is not. What is the PCIe 5 version based on memory? 4 bytes. Transfer mode. What is the speed of CXL 3.0? Oh, we see. We have a 121. So 128 with CXL 3.0 and PCIe 6.0. We can achieve get that power throughput. Okay, reply. Please refer to the wiki. Here's the wiki. And so please refer to the wiki. All right. Concurrent. for now I'm having switches.这个为什么要改？8:35，我也不知道他有没有去。好，好的。哎呀，看我还是不给改的。That I'm here without you. I need to be the one who takes you home. Support mode right now. doing great. Oh, alright. I didn't do much thing today. I want to write in YCSB, but let's start today's recording. Okay, I want to sleep. Bye bye.